Hi, my name is Kiran Baburaj. Welcome to Career Campus Pro YouTube channel. In this video, we will visualize two different implementations of classic stack data structure, one using arrays and the one using linked list. By the end of the video, you will understand the unique advantages and trade-offs of each approach, helping you make the right choice for your specific programming needs. First, we move on to the stack implementation using array. Here we are creating an empty stack array with a capacity of 6 elements. And we are tracking two critical pieces of information, the current size, which starts at 0, and the top pointer, which initially points to nothing since our stack is empty. The top pointer will help us to visualize where new elements go and where they are removed from. Initially, we push A onto the stack. The top pointer moves up and increase its size to 1. We place A at the top position and our stack now contains one element. Next comes B. Again the top pointer adjusts and the size increased to 2. B takes its place above A, and it's the essence of last in first out. The newest element is always on the top. We continue with C and D. We can see that each element on the stack is on the top of the previous one. With each push operation, our size increases and the top pointer adjusts the point to the newest element. Now it's time for the reverse. Let's see the pop operations in action. When we pop, we remove the most recently added element. First, we are popping the D from the stack. The top pointer moves down and the cell becomes empty, and our size decreases to 3. Notice that we always remove from the top. That's last in first out principle in action. Now we are removing C. Again the top pointer adjusts downward, the element disappears and our size decreases to 2. If we continue popping, we would remove B and A in that order, the reverse of how we were added. So we have used this fixed size array with maximum capacity of 6 elements. The top variable always tracks the index of the last element added. Both push and pop operations have order of 1 constant time complexity. Now let's look at the actual code implementation. Here is our stack class with all the essential methods. We start with the constructor that initializes an empty list to serve as our stack. The isEmpty method simply checks if the length is 0. The size returns the current number of elements, and the peek method shows us the top element without removing it. And the push method adds an item to the top, and pop removes and returns the top item. Our core operations push, pop, peek and size runs in order of 1 time, that is the constant time complexity, meaning that no matter how many elements are in our stacks, these operations always take the same amount of time. Next, we are exploring the stack data structure using the linked list for the flexibility and elegance. So let's start the visualization. Initially, we have an empty stack. Our top pointer is initially set to null, indicating that there are no elements. We are also tracking the stack size, which starts at 0. The empty state is the foundation for all the subsequent operations. Each node in our linked list has two parts, the data component represented by the circle and the next pointer with a rectangle. The data holds our stored values while next pointer creates the chain that links our nodes with the proper stack order. First, we create the first node A and its data. The top pointer now points to this node and our size increases to 1. Since it is the first element, the next pointer remains null. For B, we create the new node and makes its next pointer point to A. Then we update the top pointer point to the B. This is the key to our linked list approach. Each new node points to the previous top node. We continue with C and D. Watch how new nodes become the new top with its next pointer linking to the previous top. This creates the chain of nodes with the most recently added elements becoming the top always, perfectly maintaining the LIFO principle. Now let's explore the pop operation. When we pop from the stack, we need to remove the top element and update our top pointer to the next node in the line. When we pop D from the stack, we simply move the top pointer to the node that D was pointing to. In this case, it's C, and D node fades away and our size decreases by 1. Similarly, we pop the C. This mechanism ensures the LIFO order. Here we have dynamic sizing, no fixed capacity like the arrays, the top pointer always tracks the most recently added elements for constant time access. Each node contains both data and pointer to maintain the chain. Alright, let's dive into the code. We first define our node class with two key attributes, the data to store the value and the next to reference the next node in the chain. The stack class maintains two important properties, top to track the most recent node and the size to count the number of elements. Our methods include isEmpty, which simply checks if the top is none, getSize, which returns the size counter, peek, which returns the data from the top node when available. Further, moving on to the push method. It's demonstrate how the power of linked list approach when we push a new element. First, we create a new node with the provided data. We point the new node's next reference to current top. Next, we update the top pointer to this node and we increment our size counter. Next, the pop operation, which is equally efficient. First, we check if the stack is empty. If not, we store the top node's data. We move the top pointer to the next node in the chain and we decrement our size counter and finally return the stored data. This linked list implementation offers several key advantages: the order of one time complexity for all core operations, dynamic memory allocation since no predetermined size limit, memory efficient as we use only what we need, and no need of expensive resizing operations, and perfect for LIFO behavior throughout the node chain. And this is simple, elegant code that is easy to understand and maintain. Both the array and linked list implementations have their place in Programmer's Toolkit. The array-based stacks offers simplicity and cache efficiency, while linked list stacks provide unlimited growth and constant time operations regardless of the size. The choice between these implementations depends on the specific need. If you found this video helpful, please don't forget to like and subscribe. Happy coding. Thank you.